In the lee of the Rocky Mountains, on a clear day like this, you hear the singing of birds. Electronic ears, responding to frequencies our own ears can't detect, would hear something else. This buzzing noise is the voice of a wind profiler. The antenna both speaks and listens, and a computer interprets. How can such a strange-looking array of crisscrossing pipes possibly measure the winds above ground? I'm Tom Schlatter. I work with the Program for Regional Observing and Forecasting Services in Boulder, Colorado. I've been involved in a training program on the use of wind profiler data. This will be an introduction to the wind profiling system. We're going to discuss the wind profiling radar, how it works, what it measures, when we can expect to have a good measurement and when not. We'll talk about the accuracy of those measurements. Dr. Richard Strauch of the Wave Propagation Laboratory will be talking to us on the wind profiling system. He has helped to design and build wind profiling radars. What is a wind profiler?
A wind profiler is a type of clear air Doppler radar. That is a radar that measures in the clear air rather than what you're used to seeing in the precipitation that a conventional weather radar measures. And the wind profiler uses the Doppler radar to measure winds, vertical winds and horizontal winds, at different altitudes in the atmosphere. And it does this continuously, it does it automatically with no human intervention, and it does it with an update time that is an averaging time between 5 minutes and an hour. So it's somewhat different than the types of conventional weather radars that you may be used to.
How does a wind profiling radar differ from a conventional weather radar?
Well, the wind profiler radar differs primarily in the wavelength. We're using a much longer wavelength with the clear air Doppler radar wind profiler than a conventional radar, primarily because we're looking at clear air rather than precipitation. So we're using 75 centimeter wavelength radars in the new NOAA profilers as opposed to 10 centimeter weather radars such as NEXRAD will be. In addition, the antenna is not mechanically moved normally for the wind profiler, whereas as you know, in the conventional weather radar, you're trying to scan the whole hemisphere, so you have a mechanically moving antenna.
What are the main components of the wind profiling system?
Well, since this is a radar, the main components of the wind profiler are about the same as the components of a radar. That is, we have a transmitter, and these are pulse transmitters because there's our pulsed radars. We have an antenna that we talked about that is somewhat different, but basically the same function as a conventional radar. We have a receiver, data processor, and then a computer which controls the system and contributes to data processing. So it's very much like a conventional radar or an NEXRAD Doppler radar in terms of the main components of the system.
How does a non-moving antenna work?
Well, we have to steer the beam to about at least three beam pointing positions to measure the vector wind. We have to look vertically to measure the vertical wind, and we have to look off axis to the north and the east to measure the east and north components of the wind. And we do this with what's called a phased array antenna. That is, that different parts of the antenna are excited with different phases. And the resultant combination of the summation of all the infinitesimal elements on the antenna radiating point the beam. And this is what we call a phased array antenna. So it's basically steered by phasing different parts of the excitation on the antenna.
How does the antenna aim the beam?
The antenna aims the beam by changing the phase of excitation in different parts of the antenna. For example, suppose that we had an antenna that was pointing to the vertical, that is, it was laying flat on the ground with its mechanical axis pointing vertically, and we wanted to point the beam vertically. Then in that case, we'd excite all portions of the antenna with the same phase, and the beam would be pointing vertically just as it was an ordinary antenna that you're used to. On the other hand, if we want to steer the beam now, what we do is we keep the antenna still with its mechanical axis pointing vertically, but we point the electromagnetic axis by changing the phase of excitation. And we do this by keeping the phase the same in a row of elements along the antenna, but from row to row, changing the phase. So in that way, we retard the phase in a particular direction, and that tilts the beam in that direction.
This is a view of the profiler from the side. We're looking down 4 rows of radiating elements, which make up part of the antenna. The transmitted pulse enters at the bottom and travels through cables to the radiating elements. In this case, the cables are all the same length, and so the pulse reaches each row of radiating elements at the same time, in phase. Since the wave fronts are essentially horizontal, the energy in the pulse travels vertically. In this case, the pulse travels through cables of different lengths. The lengths are chosen so that the pulse reaches radiating elements on the left first. It reaches radiating elements on the right later, and so the phase is retarded from row to row. By regulating the phase in this way, the wave fronts are made to slope toward the right, and the energy propagates at an angle to the vertical. Is the antenna always sending in all directions?
No, for example, when all the elements are fed in phase and we have a beam pointing vertically, then we're only pointing in the vertical direction, just as it would be an ordinary antenna. So what you might think of as different elements of the antenna might be transmitting into a wide variety of angles. When you sum all the elements, you add the elements all in phase, they'll only add in phase in the direction that you want. So we really point in only one direction at a time, but we select that pointing direction electronically by phasing.
How much power is required to operate the antenna?
Well, with one of these wind profiler radars, the important power is the average power, not the peak power. Normally you're used to thinking of power with radars in terms of peak power being important, but with these kinds of radars, it's average power that's important. And the wind profiler radar network that NOAA is procuring will use 20 kilowatts of peak power and between 500 watts and 2 kilowatts of average power. You can contrast that with the NEXRAD, which uses a megawatt high power, megawatt peak power, and about a kilowatt average power. So average power is about the same as NEXRAD. Peak power would be much less. But therefore, we're using, with the wind profiler, much higher pulse repetition rates. We're using longer pulses to get that peak power, to get the average power that we want.
How much time is the antenna transmitting and how much time is it off?
Typical on-off time is similar to the NEXRAD radar. For example, in the NEXRAD radar, you're used to 1 microsecond pulses every millisecond. Here we're talking about pulses that might be the order of 4 microseconds every 100 microseconds. So roughly a duty cycle of 4% rather than a 10th% like for a NEXRAD.
How much power comes back?
Well, if we would send, for example, 20,000 watts of pulsed power output, we would expect to get back something like minus 100 to minus 130 dBm, which is decibels below a milliwatt. And in terms of actual power, that's 10 to the minus 13 to 10 to the minus 16 watts. So we're talking about roughly 20 orders of magnitude less power coming back than was sent out.
If so little power comes back, how can we get any useful information out of it?
Well, as we said earlier, we have only three to 5 beam pointing positions. And this means that we can spend much more time and averaging time and data processing time looking in a particular direction. So for example, we might process the data from one beam position in roughly a minute. But during that minute, we will use roughly a million transmitted pulses to get the information. Whereas, for example, an NEXRAD would only use roughly 100 pulses to get the information, and then it would move to a new pointing position. So it's averaging time and data processing which allow the wind profiler to operate with very weak signals.
What causes some of the transmitted energy to come back to the antenna? Or in other words, what does the profiling radar see?
At night along a cool garden or along a creek bed, you can actually feel the temperature difference as you walk along. And this is the same thing that we're seeing with the radar, except very much smaller scale sizes in space and in amplitude. A best example or analogy we can have for the scattering mechanism is a transmission line. If you consider a perfect transmission line and you send a wave or a pulse along a perfect transmission line, it'll propagate along that transmission line to a load with no reflections. But if you think for a minute of a transmission line where it was made imperfectly so that something was wrong perhaps with the inner conductor, and then we would look at what we call the impedance of that cable, and it might change a little bit. And because of those changes, when the wave pulse propagated along that cable, there would be minute reflections back toward the transmitter. And that's the same analogy that we have with the clear air radar.
Is there any size of eddies that the radar is particularly sensitive to?
Yes, the radar is sensitive to those scales in size that are half the radar wavelength, which means roughly 35 centimeters for the 75 centimeter NOAA wind profiler radar. So that's the scale size that the radar is sensitive. So if you consider all of the fluctuations that take place as a function of space, if you Fourier analyze these, you'll look at that component, which is at half the radar wavelength, and that'll tell you how much signal the radar will receive.
Under what conditions can we expect to derive a valid wind measurement?
Okay, we expect that the radar wind profiler should be able to measure winds from a few hundred meters above ground, and we're hoping for about 500 meters above ground for the new NOAA network, to 12 to 14 kilometers above ground typically. We would expect that radar to measure to wind profiles to 16 kilometers above the ground quite often, but in certain weather conditions it will be struggling to get 10 kilometers altitude. And those particular conditions when the profiler will work poorest are in cases where we have high pressure and light winds, fair weather cases. Now, we don't expect the radar to work in thunderstorms. And the reason, of course, in the thunderstorm is that the beam pointing directions that are necessary to measure the wind means that we're pointing in different places in the thunderstorm. And you can just imagine how much variability there is in both time and space. So even if the radar made a good measurement at a certain altitude to the zenith direction and toward the north direction, toward the east direction, they would be meaningless if you tried to put them together in the thunderstorm. It just will not expect to work in a thunderstorm. There are other cases where we'll have some trouble. Aircraft interference, for example, will cause loss of data. Ground clutter is a problem. Radio interference can be a problem. And probably the one problem which will be most difficult to solve totally will be what we call the side lobe problem. That is, the antenna points in a particular direction, but it has side lobes which point at weaker, smaller amounts of energy in other directions. And if one of those side lobes should be looking at a strong signal, for example, a rain shaft, while the main beam was receiving signals from the clear air, we might have the case where the rain signal through the side lobe was stronger than the desired signal through the main lobe. And in that case, we would have a problem, a serious problem.
Is there anything we can do about spurious returns, seeing things that we're not interested in seeing or don't want to see?
Yes, we have to develop, and we're continuing to develop algorithms, which we call quality control algorithms, that'll be based on time and height continuity primarily, and realistic parameters that the wind can have. That is, we can't accept data that gives an unrealistic wind shear. So we have to develop post-processing models, post-processing algorithms that we can basically edit data to reject outliers that we know are unrealistic.
What happens if it's raining?
Okay, in rain, let's go back to the case of, let's start with the case of stratiform rain or snow, widespread precipitation, where we know that in time and in space, things are fairly uniform. In that case, when we point the antenna to the zenith and to the north and to the east, we expect to see the same general wind conditions in those volumes. When we see that, then the radar will work much like an X-rad radar, measuring the radial velocity and generating an accurate horizontal wind profile. However, we will not get the vertical wind because the radar will be measuring the particle fall speeds. So what we'll get in that case is particle fall speeds and instead of vertical wind, but we will still get good horizontal winds. And of course, we must have that kind of situation because the radar has to work in a place like Seattle in the wintertime where we expect drizzle or light precipitation almost for the whole winter. We'd have to have the radar being able to handle that situation. The situation we can't handle is a thunderstorm case where we don't have time and space continuity or time and space uniformity of the winds.
What happens if the rain is falling in a downdraft? The radar is sensitive to the fall speed of the raindrops, but it can't apparently measure the speed of the air in the downdraft. What do we do then?
Well, it's still the same situation. If the downdraft extends for all the three beam pointing positions, that is the same vertical wind exists at the three beam pointing positions, everything will still be all right. We'll get good horizontal winds, not good vertical winds. We'll get the fall speed plus the vertical wind in this case. But the horizontal winds will still be good if we have the temporal and spatial continuity. So it's the spatial continuity that is required. We're making an assumption of a uniformity at the beam pointing positions.
What is the accuracy of the profiler winds?
Well, based on the measurements that we've made and with research devices, we expect horizontal winds to be of the order of a meter per second accuracy of an order of a meter per second, somewhat better in higher signal noise ratio, which we'll have at lower altitudes, a little worse at lower signal noise ratio at higher altitudes. The vertical wind accuracy will be the order of 10 to 20 centimeters per second, averaged over an hour, and that then will require, if you want to get down to 3 to 4 centimeter per second accuracy, averaging over a number of hours of observation.
How can we estimate the accuracy of the profiler measurements?
We've estimated the accuracy based on comparing profilers with each other, comparing profilers with radiosondes, comparing profilers with aircraft measurements. Primarily, we find the best way is to compare the profilers against each other, because we can get the data automatically and continuously, whereas if we do it with radiosondes, we only get a chance now and then to get a measurement.
Thank you, Dr. Strauch. We're near Platteville, Colorado, about 30 miles north of Denver. Here, NOAA's Wave Propagation Laboratory has been testing wind profilers since 1981. WPL chose this remote site because it is relatively free of the radio frequency interference usually found near cities. In addition, the flat terrain helps minimize ground clutter. This is the first of 31 profilers being installed in a network covering the central United States. Installation of the network will be complete by mid-1990. Let's examine the antenna more closely. We're viewing one section of the 404 megahertz antenna. A coaxial cable runs the length of this section. Coaxial means that the cable has an inner conductor and an outer conductor. Note that the cable is not continuous. Every half wavelength, every 37 centimeters, the inner and outer conductors are interchanged. Because of this spacing, the current in all segments between interchanges is in phase, and the cable acts as a row of half wavelength elements, all radiating in phase. A series of rows oriented parallel to this one is used to aim the beam vertically. If all rows radiate in phase, the beam is vertical. The same rows can also be used to aim the beam off vertical. When the phase is retarded from one row to the next, the beam points at an angle to the vertical, say toward the east. A coaxial collinear antenna aligned in this way can point straight up and toward the east, but it cannot point toward the north. For this purpose, a second antenna can be aligned at right angles to the first. In practice, the second antenna rests on top of the first one, forming a square array of cables. This causes no problems because only one antenna operates at a time. When the pulse is fed to rows of the second antenna and the phase is retarded from bottom to top, the beam points toward the north. In this view of the real antenna, fiberglass tubing covers all the cables to protect them from the weather, and black clamps hold the assembly together. We can visualize the energy radiated by the antenna and backscattered by the atmosphere on an oscilloscope. Doug Vandekamp of NOAA's Profiler program explains.
This is the lowest height that we start sampling the data at, which is 500 meters above the ground, which is back here. And then we sample every 250 meters in height. We cannot sample the signal atmospheric echo any lower than here because you are in the transmitter recovery here. There's no atmospheric echo contained in this. The only atmospheric echoes are out in this area here. So you're restricted to your minimum range, which is right here. This is the transmitted pulse that comes out from the transmitter into the antennas. We receive this signal back from the antennas into the receiver. We start sampling the data in this area here and get good results in this noise level out here. The atmospheric echo is actually contained in the noise level here. By long-term averaging on the order of minutes, we can extract the atmospheric echo and tell what the winds are.
This is what happens when an airplane flies through the beam.
There it is. So this airplane is wiping out the data at these range gates because the signal is so overwhelmed.
Is that it again?
Yep, very strong. So if we looked at the raw data that's going to come out from this averaging period, you'll see very wild numbers that would not match with anything you would expect.
Let's review the major points of this program. The wind profiler is a Doppler radar that points in 3 directions sequentially, vertically and 15 degrees off the vertical, usually toward the north and east. The main components of the wind profiler are the power supply and transmitter, the antenna, a fixed phased array antenna, and a receiver and computer. The antenna consists of an array of radiating elements. It doesn't move. It aims the beam by changing the phase of the transmitted signal at each row of radiating elements. When the pulses arrive at all rows in phase, the energy propagates vertically. When the phase of the pulses is retarded from one row to the next, the energy travels at an angle to the vertical. The profiling radar measures the radial velocity in each pointing direction. From these measurements, it is possible to compute the horizontal wind at many levels in the vertical, with an accuracy of about 1 meter per second. Wind profiles are available every hour and can be displayed in time-height cross-sections like this one. The transmitter of the profiling radar uses 16 kilowatts of peak power when it is emitting a pulse. Of that amount, only a very tiny fraction comes back. Turbulent eddies carried by the winds aloft scatter the energy back toward the radar. The profiler points in the same direction and transmits in the same mode for about a minute at a time. Depending upon the mode of operation, either 6,500 or 10,000 pulses are emitted every second. Thus, the wind passing through the beam during a minute is exceedingly well sampled. Extensive time averaging of the returned energy makes it possible to separate even a very weak signal from the ever-present noise. The horizontal separation of the beams increases with altitude above the ground. At 10 kilometers altitude, the separation between the beams is illustrated here. As long as the wind is uniform across all 3 beams, the profiler can render a valid wind measurement. But if the wind varies in between the beams, no valid measurement is possible. Thunderstorms greatly disturb the local wind field. Thus, the profiler cannot accurately measure the wind when thunderstorms pass through any of the 3 beams. During steady precipitation, the profiling radar will normally sense the fall speed of raindrops or snowflakes, rather than the vertical motion of the air. Even so, as long as the fall speed is uniform across all 3 beams, the profiler can still accurately measure the horizontal wind. During showery weather, the condition of uniform fall speed is violated. This has been a brief introduction to the wind profiling system. It really helps to understand in detail the instrument that's providing the data that we use to make forecasts. In future sessions, we'll talk about quality control procedures, and we'll discuss how to use wind profiling information in summertime and wintertime forecasting.